This lesson follows on from the ideas of pressure, but now we're turning more towards looking at how gases exert pressures, and this one will be known as the pressure law. So we looked at last time how gases exist inside a box, and this is looking at how the pressure changes with gases that are at different temperatures. So let's just remind ourselves of what happens inside a box. So we have a gas particle, and it's flying around. We know that these are particles because of Brownian motion showed us that. And they're flying around and bounce off the sides of the walls. Now we've got to feel for what pressure is, but let's just remind ourselves what temperature is. Because we can easily be confused about what temperature is. Temperature talks about how fast these particles are moving. And if we're talking about how fast they're moving, technically we should talk about their kinetic energy. So there will be a range of them. So temperature is related to the kinetic energy. Of course, they're not all going to go at one speed. Some might go faster than others. Some might go at slow speeds. Others might go at very, very, very fast speeds. But you will always have just one temperature. So it's important to understand here that temperature relates to a per particle. So you're interested in just one particle, but it's the average kinetic energy per particle. So therefore we usually put these little signs around it. So temperature is actually, how as we define it, is the average kinetic energy per particle. That's a really, really important definition to learn. It also suggests why that if we have, for instance, this is just an aside, if we had a cup of tea sitting at 60 degrees and we had a bath of water at 40 degrees, or let's just say 60 for the sake of it, and what's similar about this and what's different about this? Well, the similarities would be if you just looked at one particle, on average it would have the same kinetic energy. However, the bath of water, because there's so many more of them, it has a bigger energy, so the energy of the bath of water is greater. But the particles are the same. Okay, so just a little aside. However, let's go back to this instance here. We're saying if the temperature increases, then what we're really saying is, on average, these have a greater speed. And therefore, what effect does that have on the pressure? Well, hopefully you'll appreciate that if it's moving faster, so if the temperature increases, then that means the speeds increase, because the speeds and kinetic energy are very, very closely related. That means that they collide with the walls more often and with more force. And therefore, if we have a greater force, therefore the pressure increases, because we know how force and pressure are related. So essentially, as temperature increases, the pressure increases. And so much so that actually if you double the temperature, we double the pressure. And all of that comes together quite nicely in a law, which is the pressure law on the top. So what we're saying is that temperature is directly proportional to the pressure. Or T is proportional to P. Or mathematically, we could write this as T equals a constant times P. And just the last step of the way, we say to ourselves that temperature divided by the pressure, if I shift that down underneath, is equal to a constant. Now that is the idea behind the pressure law. The temperature divided by the pressure is equal to a constant. Or, indeed, if you prefer, we could write it as the pressure divided by the temperature is equal to a constant. We're not too worried about what constant is, but we know it's going to be constant so long as the one proviso is the volume is the same. And we'll come back to the volume later. But so long as the volume is the same, this remains constant. So what we say is before is going to equal to a constant, and also afterwards is going to equal to a constant. So therefore, if this is all before and that's after, this is the relationship that explains the pressure law. And we're going to use this to explain and to work through some problems in a minute. However, there's a couple of things to talk about here first of all. First of all, what happens if the temperature is 0 degrees Celsius? If we have 0 degrees Celsius here, suddenly the pressure divided by 0 mathematically takes you to infinity. So it's important to say that these temperatures here, the only time it goes to infinity is if the particles stop moving. The temperatures must be in Kelvin. Why in Kelvin? Well, as I mentioned, because otherwise you get this mathematical anomaly. It's also important because if we're saying the average kinetic energy per particle is the temperature, if it does not move, it has no temperature. So therefore, we know that particles do move at 0 degrees Celsius. We need to reinvent a temperature scale in which 0 degrees Kelvin means that the particles are not moving. And any temperature above that means the particles are moving with an increased kinetic energy. In other words, our temperature scales, let's write it here, they are still a centigrade scale, i.e. they're moving up by hundreds, but are 0 degrees Celsius and onward to 100 degrees Celsius, and all the way back to minus 273 degrees Celsius. This point, absolute zero, is where our Kelvin scale starts. And as you move along, it's just a simple conversion, because the same units are appropriate to both sides of this scale. 373 Kelvin. So this is Celsius and Kelvin. Okay, so I hope that temperature scale makes sense. And we will be using Kelvin in our equations. Good. Okay, then let's just make reference to one last thing. If we were to plot the pressure against the temperature in Celsius, then what happens is we find ourselves with a graph that looks similar to that. Meaning that at 0 degrees Celsius we don't suddenly lose pressure, there is still a pressure exerted. However, when we track this back, the point at which there is no pressure is minus 273 degrees Celsius, or 0 Kelvin. So that's a really important little point to bear in mind. Now, you might say to yourself, well, I know that the pressure decreases when it suddenly becomes a... We're not talking about changes of state here, we're just talking about the movement of particles. Okay, then let's use this equation and see how it works and see how it pans out. Let's go with a first example of a Coke bottle, a 2-litre Coke bottle, this stays constant, the volume stays constant. However, its initial pressure is at 1 times 10 to the 5 pascals, and its initial temperature is 17 degrees Celsius. We then heat it, and the temperature then increases to 87 degrees Celsius. So what is the new pressure? Now if you think you know the answer, then hit pause. Otherwise, here comes the solutions. Okay, let's start with our equation for the pressure law. Now we can rotate these. This can be any way up, as I've shown you before. However, this time I'm looking for P2. So in that case, I need to get rid of that T1. So I multiply both sides by so. Right, and then a simple substitution is needed. However, be careful here. We need to convert the temperatures into Kelvin. And this becomes 87 plus 273 Kelvin. So therefore, my first pressure is 1 times 10 to the 5 divided by 273 plus 17 multiplied by 273 plus 87, and that gives me a grand total of about 1.2 times 10 to the 5 pascals. Okay, so the first trick there, manipulating the equation, and the second, making sure you get the right temperature. Okay, let's imagine we keep heating. And it explodes when the pressure reaches 1.5 times 10 to the 5 pascals. What temperature does it reach? If you think you know the answer, hit pause, otherwise here comes the solution. Right, now I'm looking for the temperature, of course, so therefore I'm going to write the temperature first. So T1 over P1, which is perfectly okay. T2 over P2. And now, of course, I'm looking for what temperature, temperature 2, so I'm going to get rid of that P by multiplying through temperature 1 divided by pressure 1 times pressure 2 gives me temperature 2. Okay, temperature 1 was initially, we're talking about, so we're going back to 273 plus 17 divided by the pressure 1, which was 1 times 10 to the 5, multiplied the new pressure, which is 1.5 times 10 to the 5. And that gives me a grand total of 435 Kelvin, which is the same as 162 degrees Celsius. You might say to yourself, how on earth could Coke get up to that temperature? Well, when you are putting it under pressure and the volume is holding it, it has a higher boiling point. Okay, let's look at a few more examples just to make sure we're comfortable with that. Much more straightforward this time. Let's just throw in some numbers here. We have initial pressure is 40 kilopascals at a temperature of minus 73 degrees Celsius, and we're going to heat to 327 degrees Celsius. What is the new pressure? Think you know the answer? Hit pause, otherwise here comes the solution. Okay, so I'm looking for the new pressure, so I'm going to keep P's on the top. I'm looking for the new pressure, P2, so I need to get rid of the T1. Okay, then so P1, T2, T1, and then substituting the values. Now, so long as you keep the K in there, I mean, I don't advise this for all equations, but so long as you keep the K in there, you know the answer will come out as kilo. First one, 273 minus 73. Divide that by the temperature of 273 plus 327. And my answer comes out to be 120, so therefore kilopascals. Good. One more. Let's just make sure we're happy with the next one. Okay, what do we have? We have initial pressure of 150 kilopascals with a temperature of 450 Kelvin. And the pressure reduces to 100 kilopascals. What's the new temperature in degrees Celsius? Think you know the answer? Hit pause. Otherwise, here comes the solution. Okay, I'm looking for the temperature afterwards. So I'm going to put T1 over T2 is the same as T2 over P2. Get rid of my P because I want that on its own. So therefore T1 P2 over P1 gives me T2. And let's substitute in. So my first temperature is 450 Kelvin. It's been done for me. That's great. 150 kilopascals are in there. Divide it by 100 kilopascals. And bearing in mind here, I've gone from a higher pressure to lower. I know the temperature out is going to be lower. And that gives me, let's quickly do the sums. I forgot to do the sums. .300 Kelvin, which is the same as 27 degrees C. Okay, so long as we just bear in mind this relationship, then all is okay. And as long as you can explain that if you were to double the pressure, then you have achieved that by doubling the temperature in Kelvin, the rest should make sense.